Okay, good morning, everyone. You can hear me in the back just fine? Okay, so a couple announcements as we get started this morning. Remember, we have our quiz on the data storage unit here in about an hour. So we'll finish up our unit on data transmission and then have our quiz. The homework on this data transmission unit is now posted. Remember that it's going to be due on Tuesday morning this week, not Monday morning. Remember that over the weekend, both David and I are going to be very, very slow to respond to emails. We're both out of the office the next couple days. So the homework, if you've got any questions, it may not be until Monday that you get a response, but bring your questions to class Monday morning, post them on Blackboard. We will respond to them, but it may be a couple days before we have a chance to do so. And that's why the homework will then be due Tuesday morning rather than Monday morning, when it normally would be. Solutions to that homework assignment will be posted Tuesday after the homework is due. Please review them, bring questions to class on Wednesday, and we'll have the quiz on that unit next Wednesday. Okay? Any questions sort of on the logistics there? Okay. Then if not, does anybody have any questions over anything we talked about on Monday? Okay, so remember last time we're working on this data transmission unit, and our big question was, how do we guarantee or how do we know that the message that we send, whether it's through text messaging, through email, through any of these different venues, is actually the message that's received on the other end? And the two sort of sub-questions that we had to deal with this were, number one, how do we figure out how many errors do we expect during a transmission? Because if we have a relatively low number of expected errors, that may lead us to think about, well, how do we handle the errors differently than if we think we're going to have a really high number of errors? We can develop sort of maybe different problem-solving approaches depending on which of those regimes we're in. And so we spent most of the lecture last time looking at probability and statistics, trying to answer how do we understand how many errors we might see in a particular message. Remember, we had that example where I had my 3 megabyte file. It was an image. We wanted to text message it. And did that really work? Was that a good thing? No, it didn't get through. And so what we're going to see today, and sort of just to recap from last time, is the way this is going to work is we're going to take whatever our total message is, whether it's that 3 megabyte file, whether it's text, whether it's something else, and we're going to break it up into lots of shorter pieces, okay? With the idea then that we would expect fewer errors in a shorter message than we would in a longer message. Again, just think back when we were talking about that binomial distribution last time, our expected number of errors was equal to the number of trials, or that is the number of bits, times the probability that you get an error on any one bit. So if we have a shorter message, we have a smaller number of errors, which means if that error creeps in, we know it's sort of localized in some region, which might make it easier to correct or easier to fix. And so that's where we're headed. And so to sort of get us starting to think along those lines, our very final example last time was to say, well, let's just consider sending 7 bits. Instead of these 25 million odd bits we had in that 3 megabyte file, let's just look at 7. Maybe put a little bit more realistic of a probability on there, just to say there's a 75% chance that each bit gets transmitted correctly. And we could ask ourselves, using again that binomial distribution that we discussed last time, what was the probability that your friend receives the message with exactly 1 error? And we could go through, we did this example last time, and it ended up being about 31%. Which is maybe not the likeliest outcome, but it's not, I don't know, 1 in 3 chance doesn't strike me as being that unlikely. Okay? And so then where we're going today is now that we've understood that if we think about having some of these smaller messages where we've broken everything up, where there's a relatively small number of errors, how can we try to account for that and design other tools in place such that if an error creeps in, we can first of all detect it, but then in some cases we might actually be able to correct for it as well. Okay? And so that's where we're headed today. Again, does anybody have any questions before we jump into some new stuff? All right. So then, one possible way to deal with errors. So now we're going to sort of leave the probability behind for today, and we're going to talk about what we'll get to is information theory here in a little bit. But the idea is now you've sent the message to me, I've received it, and I think there's an error. How I reach that determination, we'll come back to that momentarily. But the question is now, how do we go about fixing it? And so one of the easiest examples that we've seen is, well, I could just tell you, say, hey, there was an error in that transmission. Can you resend it to me? And in a lot of cases, that's not necessarily a big problem, but in other cases, it might be a huge problem. And so, generally speaking, we want to try to reserve that idea of resending the message for really worst case scenarios. When we absolutely have no idea what else to do, we'll go back to the sender and say, hey, send that to me again. And so what we're going to think about today is, instead of having to do that, what if we modified the message that you were sending me a little bit and try to include with those modifications a little bit of extra information that basically is going to give me some context. What is it you were trying to send? So that if I can detect this error, do I have some idea how to correct it, rather than me having to say to you, send that message back? Maybe I can determine from this extra information what you actually meant to say, and then I can just interpret what you sent, correct the error, and there's no resending. And an example of this was sort of in these phonetic alphabets that we saw this time last week, where, again, we were picking on November last time. But if you were going to send a message to me using the phonetic alphabet, and I hear amber, do I know you said November? Yeah, because nothing else on that list sort of ends in ember. And so even though I didn't actually hear the N, I didn't hear the full word November, I was able to determine, oh, I think I know what you meant, because there was that extra context that you put in there. And rather than having to tell you, hey, repeat your message, I just know, oh, that was an N. And I can move on. And so what we're going to do is start to think about these same types of ideas, but how can we put them and use them to understand binary codes and binary messages? So we're going to need a little bit of some background, just very briefly, called binary algebra, or binary addition. We saw this and mentioned it briefly in the last unit on data storage, but just to sort of codify it a little bit more, where we say if we take 2 bits, so we've got our zeros and our ones, and we want to add them together, what do we get? And so if you think 0 plus 0, if we add those, we should get 0. And if we have 1 plus 0 or 0 plus 1, we should get 1. And the only sort of tricky case is here, if we want to add 2 ones, well, nominally, if we added 1 plus 1, we would expect 2. But can you represent 2 using only 1 bit? No, you need 2 bits. So what we're going to do is then just say, well, if we have 1 plus 1, we're just going to call it 0. Okay, so think about, you carried the 1 into the 2's digit, but you can't actually store the 2's digit, so we just throw it away. So then for a question to sort of just get us warmed up here, what would be 1 plus 1 plus 0 plus 1 plus 0 plus 1? Take a moment and think about what that might be. Okay, well, so this is a binary addition, so the answer has to be either 0 or 1. So who thinks it's 0? Okay, anybody think it's 1? A few people. Okay, so we can go through this sort of step by step and see what's going on, and just sort of go along digit by digit. So if we have now this first 2, this 1 plus 1, that's going to give us, that's a 0. So now we have 0 plus 0, which gives us 0. 0 plus 1 is 1. Okay, I'm going to carry this up here, just make space. 1 plus 0 is 1, and 1 plus 1 is 0. So the total answer, when that's done, when we take that binary sum, is going to give us 0. A good rule of thumb when looking at these binary sums like this is, rather than having to go through and add up each of these bits, all you necessarily need to do is count how many ones digits there are in that sum. If there's an even number of ones, what's going to happen? You're going to come out to 0, because every pair of those ones is going to cancel and return you to 0. If there's an odd number of ones, then the total sum is going to be 1, because the even pairs will cancel out, and then there's 1 left over. And so sure enough, you can see in this example there were 4 ones. That's even. And so our total answer was 0. Okay, so starting off a little bit simply, we're going to talk about a couple different types of codes today, what's called an error detecting code, and then we'll get into an error correcting code in a little bit. But the idea behind all of these is we're going to put some extra information into our message, but we're going to do it in what might be something of a clever way. So we're not just going to sort of randomly throw extra bits into our message. And when we think about an error detecting code, basically our goal is we want to say, well, how can we design this extra information, what we're going to add, that's going to help us somehow detect, did an error creep into that message? while it was being sent from you to me. And so there's no unique way to do an error detecting code. We're going to talk about one specific example. And in particular, what we're going to look at today is what's called the checksum. And so just as we've got here on the slide, the checksum of a message is just the binary addition of all the bits in the message. So take whatever your message is, add it together bitwise, just to say, look and see, do you have an even number of ones or an odd number of ones? And that bit that comes out is called the checksum. So if we had a message, say, 1101, what's the checksum of that message? It's 1. Well, we can look and see how many ones are there in 1101. There are 3. That's an odd number. So when we do that binary addition, that's a 1. And so if we think about another example, what about 1111? What's the checksum there? It's 0, because now we have an odd number of ones, or excuse me, an even number of ones. And so one of the things that's sort of neat about the checksum is look at those two messages now, the 1101 and the 1111. What's the difference between those two messages? How much changed? Just 1 bit. Okay, notice that third bit flipped from a 0 in the first message to a 1 in the second message. But what happened to the checksum between those two messages? It also flipped. So in this sense, what this might be telling us is that the checksum could be used to detect a 1 error difference. If we were to send those two messages, we would expect to get a different checksum. And so if we had actually sent 1101, but the other person received 1111, if they were to check the checksums, they might see something different. And so this is exactly how we can think about making an error detecting code. What we're going to do is say the checksum can trivially detect a single error in the message. And so what we'll do is we'll take maybe those 4 bits that were our message on the last slide, and we're going to add the checksum to the back of it when we go to send and receive. Okay, so to work through an example here, we're going to send a 4-bit message. Now, we say now your BFF receives the message 11010. Notice how many bits are there? There are 5. So what's that 5th bit? It's the checksum. Because remember, our message is actually only the first 4 bits. But we're adding this extra piece of information on the back to help us figure out what's going on with errors. Okay? So if your BFF received 11010, was there an error in the message? Yes. Because look at those first 4 digits. Remember, that's our message part. And what would we expect the checksum to be? We'd expect it to be 1, because there are 3 ones. But yet the message that they received said, we expect the checksum to be a 0. And so something doesn't match up here. Somewhere, one of the bits is wrong. Do we know which bit is wrong? Okay, so who thinks we know which bit is wrong? A couple hands go up. Who thinks we don't? Okay, a couple hands go up. Why do you think we know which bit is wrong? Which bit is wrong? Which one? Right, so the third digit could maybe have been a 1 in what we originally sent, but then the 4th one could also be a 0. But, okay, so let me build on that. Could the first one also have been a 0? Or could the second one have been a 0? Or if we really want to be sort of mischievous, could the checksum be the bit that's wrong? Could there just be an error and that checksum should have actually been a 1? Yeah. The point is, we don't know which one of the bits is wrong. All we know is that one of them is. Okay? And so this is the idea of the error detecting code. Were we able to detect the error by adding this checksum? Sure. Do we know how to correct it? Not a chance. All we know is that an error crept in. Okay, so now, suppose in a different situation, your BFF received 11011. Okay, so what are the 4 message bits in this case that your BFF received? Right, we get the 1101 being the first 4 bits that we put in here, and that 1 being the proposed checksum. Does it look like there was an error in this case? No, because we look at the checksum of those 4 digits, the 1101, and we would expect the checksum should be 1. We look at the message and it says, oh, checksum was 1. Great. So was there an error? Probably not. But are you sure? So now compare the checksum. So now we've got our 1101 here being the 4 digits that we had right before for our message. But suppose now you've also got the message 0111. What are the checksums of those two messages? They're both 1. So what if this message actually had 2 errors? So your BFF received 1101, but you actually sent 0111 with the checksum. Did you detect that error? No. Okay? Because the idea here, how many errors did we now have if the message we actually sent was 01111? How many errors did we actually have? We had 2. And so remember, this is the idea of the checksum. Every time there's one of the bits flipped, the checksum changes. So if 2 of the bits are wrong, what happened to the checksum? It reverted right back to where it started with. Okay? And so this is one of the problems we might have to worry about, is these error detecting or error correcting codes are designed with certain assumptions in mind. And when we think about using this idea of the checksum, one of its limitations is that it can only detect actually an odd number of errors. Okay, so it was really designed just to find one error, but if you happen to have 3 or 5 or 7, it'll work just fine there too. But the problem is, if we say we have 2 errors, this checksum's not going to help us at all. On top of that, it's been pretty good for detecting errors, but it's not really good at correcting them. Even if we can determine using this checksum, oh, there's an error in our message, we still have no idea which bit it was actually in, and we're going to have to go back to the sender and say, hey, can you resend that? Okay? Does that make sense? Okay, so let's look at this a little bit more. So suppose the 4-bit message we're actually interested in sending is 1101. What's the actual 5-bit message that you send? Right, so we're going to have our 4 digits, the 1101, and we're going to add to the back of that the checksum, which happens to be 1 in this case. So the message that we sent was 11011. Okay, so your BFF receives 11010. Okay, so we know from looking at this, is there an error in that message? Yep. First of all, we can just compare because we know what the message should have been. We're omnipotent at this point in time. And we could look and say there's an error, but does our BFF know that there's an error in that message? Why not? Okay, so our BFF should know that there's an error. Why will they know there's an error?
Because if you're using the checksum, you'll see that the last digit is a 0.
Right. So our BFF can look at that message. They'll take the checksum of those first 4 bits of that message and say that checksum is 1. And they're going to compare it against the checksum bit in the actual message they received, which is a 0, and they're going to realize something's wrong. There's an odd number of errors in the message. Okay? But now, in this case, where we already sort of know what's going on, where was the error? It's actually in the checksum bit itself. Were the 4 message bits actually received correctly? Yes. But does our BFF know that? No, they don't. Okay. So, alternatively, maybe your BFF received 11011. Do they detect any errors? Nope. And in this case, was that actually the correct message? Yeah. Okay. So that's cool. But what if they then received 10011? Do they detect an error? Yep. How many errors are there actually when we compare the messages? There's 1. Of course, our BFF doesn't know it, but it's in digit 2. Because we can look, we sent the 11011. Okay? And now what if if our BFF actually received 10010? Do they detect an error? No, because they look at the checksum of those first 4 digits, and they're going to see the checksum there is a 0, which matches the bit that they received in that checksum digit. Now we know, again, we know everything in this particular example. Were there actually errors in that message? Yep, but now there were 2, and that goes undetected. Again, that being a limitation of this particular error detecting code. Could we have designed a more robust error detecting code that would actually detect 2 errors? Could we have, do you think? Yeah, we could have. We just didn't. And so this comes down this idea that we can always develop more sophisticated codes. The checksum is sort of the easiest idea of an error detecting code. It only works really for one error. But if we wanted to have codes that could detect 2 errors, 3 errors, 15 errors, there's no conceptual problem. What's different? Well, it requires a little bit of linear algebra, and they can be really tedious to use. But they're not conceptually any different. So if you're interested, you can Google and find some interesting things about it. But there's usually another downside to trying to develop more sophisticated codes. And so one is, how long does it take you to encode or decode your message? Computers are really good at doing binary addition, but if they need to go through 3 megabytes of bits to do that binary addition to find the checksum, or to do something more sophisticated, that might take a little bit of time. It's not going to happen instantly. Okay? And so perhaps whatever data you're transmitting, could it be time sensitive? Can you think of a case where you need to send an email and it's critical and it's urgent that the other person get it as soon as possible? Yeah. And so do we necessarily want to have to wait for the time on more sophisticated codes? Maybe not. Maybe it's not a problem, but maybe it could be an issue. One of the other issues that creeps in, as we develop more and more sophisticated codes for doing this, we have to add more overhead bits. So we had just that one overhead bit with the checksum, which was the checksum itself. If we wanted to think about having another code that could deal with 2 or 3 or 4 errors, we're going to have to add more overhead bits. Well, that means there's more data in our message, which means there's a more chance for errors to creep in, which, okay, this starts to get into a positive feedback loop, and that's not necessarily a good thing. Okay? So there are trade-offs here. In a lot of cases, people end up wanting to use fairly simple codes because then they keep things small and the processing time is fairly short. And that's good in a lot of applications. But in theory, if you want to go a little bit higher and do more sophisticated things, there's no problem. Okay? Does that trade-off sort of make sense? That we can see? Okay. And so one of the things that can be really useful when trying to understand these error detecting, or we'll see momentarily, error correcting codes, is this idea from information theory called entropy. And I know if you've taken sort of chemistry or physics, you've probably seen entropy in terms of thermodynamics. This is a completely different idea. But the idea, so here in an information sense, the entropy of a message basically helps us understand how much of that total message carries information versus how much is sort of redundancy or overhead. So when we were using that checksum example on the last couple slides, we were sending 5 bits, and we were receiving 5 bits. How many of those bits actually carried information? Only 4 of them. That 5th bit was added as a check. And so when we would want to look at that amount of information, entropy is an idea that's going to help us to sort of quantify that. And I don't want to go into a formal definition of entropy. That's more than we need. Just think of it as sort of this idea of how much information was there actually in the message we were sending. And so as we sort of work and think about more sophisticated error detecting codes or error correcting codes, do you think they're going to have are they going to be as good, or is it going to be a little bit more imbalanced between what the message size is and how much overhead there is? We're going to have to add more overhead, which means the entropy is going to be thrown a little bit more out of whack. Do we really want there to be a lot of overhead bits? Not necessarily, because again, that's just more information that we have to send and receive through the channel, which increases the chance of an error. But maybe sometimes it's worth that cost because we can do more with that overhead information. And so one of the key things of today's lecture is there's always this trade-off. We can always make better codes, but they come with increased costs. Okay? So, any questions on the checksum or error detecting codes, the idea of them, before we move into error correcting codes? Yeah. Okay, so you were a little bit late, and can you look over the Echo lecture and bring questions on Monday? Okay. So the error detecting codes are nice because they can help us detect errors. But as we saw through some of these examples, they cannot help us correct the error. We can say, oh, look, there's an error in this message, but if we wanted to know which specific bit had the error, we have no idea. That's not something we can determine. And so what an error correcting code does is go just a little bit further. We're going to add a little bit more of this overhead or this contextual information. So there's going to be more bits that we're having to add on to the back of our message. but we're going to structure them in a way that not only are we able to detect the error, but that we can actually correct it as well. And then if we realize there's the error, we don't necessarily have to go back to our sender and say, oh, there was a problem, resend. We can just fix it. Okay? And so just as in error detecting codes, there are lots of different types of error correcting codes that have been developed over the years. We're going to talk about Hamming codes, and in particular the Hamming C74 code. Again, we'll get to that on the next slide. This was originally invented by the France Telecom back in, I believe, the 50s or 60s for the Minitel system. Has anybody heard of Minitel? Okay, one person. The guy from France. What was Minitel?
I mean, it was the ancestor of the internet.
Yep.
So basically, we had to connect from the same wire as the phone.
Mm-hmm.
And so we had some information, but it was like really expensive. But we could have access to information, for example, like what's on TV tonight
Mm-hmm.
and other information.
Yep, so basically the Minitel was a precursor to the internet in many ways, and it used sort of the phone lines to transmit data back and forth. It's only actually in very recent years that it was finally decommissioned. I think it's within the last decade or so, even though it was developed back in the 60s, 70s, somewhere in that range. But anyway, so Hamming codes were largely used there to help make sure this information that was transmitted through this internet-like thing was valid, and that you could correct for any of these issues. A different family of error-correcting codes are called the Reed-Solomon codes, developed for Professor Code. No one found that funny. Okay. Anyway, this is what was used by compact discs. Does anybody here ever use a compact disc? I want to feel old right now. Okay, good. A couple hands go up. So the idea was, if the compact disc, if there was some dust or a scratch on your disc, would that necessarily affect the music playback? Yes. And so what they would do is they would actually encode all of the data on the CD using one of these error-correcting codes so that if, as you were playing the CD, something jumped or skipped or there was an issue, the CD player could actually try to correct for that error and just play the sound that you would have gotten anyway. And so these were built in, I believe, DVDs, Blu-rays, if anyone remembers HD DVD, all used various types of error-correcting codes as well to help deal with dust or other imperfections when they were reading the discs. There's a Wikipedia page there with a link that has a whole bunch of other examples. Again, they all follow the same idea. Let's add some extra information, and we'll structure it in a way that helps us figure out what these errors were. There's also a really, really nice article that's pretty easy to read and pretty straightforward. It's, granted, 55 years old, from Scientific American there. I've uploaded it to Blackboard. If you go into the documents page for the data transmission unit, it's sort of neat. It's a fun read. A lot of what it talks about is still very accurate and very valid, even 55 years later. And to some extent, to me, it's almost a neat history experiment to see how were things published in the 60s, because the documents look quite different than what you would see in sort of a magazine or periodical today. So if you're curious, there's some more information there. So what we're going to do is we're going to look at one specific error-correcting code. And in particular, as I said a moment ago, it's the C74 Hamming code. And so what we have to deal with when thinking about this code and working with it is how do we structure those overhead bits, that redundant information that allow us to correct for errors. And as we said, there's no unique answer, which is why there's all these different types of error-correcting codes. So this looks really complicated, but I promise there's not really a lot happening here, and we'll work through this. The way the C74 Hamming code is going to work is we're going to send a 4-bit message. So whatever message I'm going to try to send to you, we're going to have to break it up into all of these 4-bit pieces. Okay? And for each of those 4 bits, we're going to add 3 bits of redundancy. Okay, is that really maybe a good ratio between information carrying bits and overhead? 4 to 3? Maybe not. That's a lot of overhead for the message size. We can develop their more sophisticated Hamming codes. You can make that ratio much better, but you need longer messages, which just makes the calculation more tedious, so we're not going to talk about those. But the ideas are just fine. And so as before, we're going to start with whatever our 4-bit message is, and we're going to append those 3 overhead bits on the back. Okay? And the last assumption that we're going to make for using this code, I've got it here in red, but I'll also highlight it on the screen, is this Hamming code assumes that there is no more than one error in the message when it's received. What do you think will happen if there is more than one error? Will this code be able to help us? Nope. Not a chance. And so this is one of the reasons why that probability theory can be useful, because if we know that the chance of having more than one error is very small, might this Hamming code be a good way to deal with any errors? Sure. But on the other hand, if we knew from probability that our chance of having 2, 3, 4, 5, however many errors was quite large, would this be an appropriate code to use? No, we'd probably want to use something more sophisticated that could handle more errors in the transmission. Okay, so the way that this ends up working is we're going to take the 4 bits of our message and we're going to call them V1, V2, V3, and V4 in order. And likewise, we'll take and we'll call our 3 overhead bits that we're going to add V5, V6, and V7. And so what we're going to do now is use the same style of binary addition that we use to calculate the checksum, but we're not actually going to look at the checksum of those 4 bits. At any given time, we're only going to look at the sum of 3 of them. And so to determine what is our first overhead bit, we're just going to add V1, V2, and V4. Notice V3 is missing. Okay? For the second overhead bit, we're going to skip V2. And for the third overhead bit, we're going to skip V1. And we'll see in a moment why that's going to be really key to how this works. And so once we have our 4 bits that we started with, we've calculated these 3 overhead bits, we're going to send a 7-bit message simply composed of V1 through 7 in order. Okay? So let's see an example. So I just repeated that block just for convenience, so we don't have to keep scrolling back and forth between the slides. Suppose now we want to encode the message 1011. Those are our 4 bits that we actually want to send that carry information. What's the 7-bit message that we actually end up sending once we put this through the C74 Hamming code? Take a moment and think about it. Okay, so what's V5 in this case? So I've already identified for you on the slides, starting from those 4 bits, we can get V1 through 4 pretty straightforwardly. What's V5 in this case? It's 0, right? Because we've got V1 is 1, plus V2 is 0, plus V4 is 1, so that basically there's an even number of 1s in that binary sum, so the sum turns out to be 0. Likewise, what's V6? V6 is now going to be 1 because we're going to add up V1, V3, and V4, which are all 1. That's an odd number of 1s. And lastly, V7 is going to be equal to 0 again, because we have a 0, a 1, and a 1. So we can now string those 7 bits together, and the message we'll have is 1011, 010. Okay? We can clean all of this up on the bottom. And that should hopefully agree with what's on the slide, and it is. Okay, so that's how we do encoding. Nothing spectacularly complicated going on. At least, I hope not. Okay, so now we had that 4-bit message, that 1011. We encoded it, we sent it. Now we're the receiver, and we've received one of these 7-bit messages. How do we actually decode it? Remember, what we want to get out is, again, what's that 4-bit message that was encoded to start with? How do we go about doing it? It turns out this is a little bit more complicated, but just emphasis on a little bit. And so what we're going to do now is we're going to follow this procedure where we'll say the 7 bits that we received, let's call them W1 through W7. Okay, again, in order. And so in principle, W1 through W4 represent the 4 bits of our message that we actually are interested in. W5, W6, and W7 are what? They're this overhead. They're this contextual information. Now the issue, though, is as the message has gone through the channel, do we know that all 7 of those bits are correct? Nope. Might they all be correct? Sure. But we don't know that. What we will assume, though, is that at most one of them is wrong. They could all be right, or W1 could be wrong, or W2 could be wrong, or W3, and so on and so forth. And so the way that we can go and check, much like we do with the checksum, how did the checksum help us determine or detect an error? We would compute the checksum of the message bits that we received, and we would compare it against the checksum that we received. And if the two matched, then we've said, oh, there's not an error. Cool. So what are we going to do? We're going to now take the 4 bits that we received that constitute what we think is the message, and we're going to compute what do we expect that redundancy, that overhead information to be based on the 4 bits that we received. And then we're going to compare that against the actual redundancy bits that we did receive to see, were there any problems? If there are no errors, what do you think is going to happen to those 3 overhead bits that we received relative to the 3 overhead bits that we calculate? They're going to be exactly the same if there are no errors. But if there are errors, what do you think is going to happen? They're going to differ. At least one of them is going to be wrong. Okay? And so what we're going to do is then go through and calculate now this big W5 is equal to our W1 plus W2 plus W4. And notice that this looks an awful lot like the procedure that we used to encode, where we said that first bit, that V5, was equal to V1 plus V2 plus V4. So again, we're basically saying, let's assume the 4 bits that we received, those first 4 bits, are correct. How would it have been encoded? Okay? And then we're going to compare and see what happens. And so we can do the same thing to get sort of this, this big W6. What do we expect that second overhead bit to be? And same thing for W7, the third overhead bit. And then where this all sort of comes out is that we're going to want to compare now these little w's. So those are the 3 bits we actually received through the transmission with the 3 bits that we calculated, which say what we would expect given the message we received. And as we go through and we look at the different combinations, we're going to be able to identify, number 1, was there an error? And number 2, based on which ones of W5, 6, and 7 don't match, where did the error actually occur? Okay? So let's try to work through this momentarily. So this slide, when all is said and done, is going to have a lot going on it, but let's talk it through in steps and see. So I've repeated the formulas up at the top for how the W5, W6, and W7 are calculated. And so, again, assuming at most 1 error, we have 8 outcomes to consider. So suppose, now, our W5s match. The bit that we received, this little W5, is exactly equal to the big W5 that we would expect based on our message. And likewise, the W6s are equal and the W7s are equal. What has to be true of those 4 original bits? Were there any errors? No. Were there any errors in our redundancy bits? No. So you hear me again? Okay. Sorry about that. Okay. So suppose now our actual W1 bit was wrong. So you sent the 7 bits, I received them, and we're going to say for the moment we know that W1 was the one that was wrong. There was the 1 error, it's in that bit. What's going to happen to our overhead bits? So when we look through the different encodings, if W1 was wrong, okay, so is W5, when we calculate that W5, is that going to be wrong? Yes, because we've changed one of the bits in that binary sum, which is going to change W5. Okay? And it's not going to match up the W5 that we got from the message, because we know there wasn't an error there, because we've already said, well, our error was in W1. Okay. Likewise for W6, is that now going to match? No. Because again, that error in W1, we're going to see right here, it's going to creep its way into that big W6, but not into little W6. And so when we compare those two, they're not going to match. And last, what about W7? It's going to be fine, because notice there's no W1 involved in W7. The one that we received is going to be still the correct bit, because we know the error wasn't there. But then the one that we calculate based on those 4 bits is also going to be unchanged, because the error was in W1. Okay? And so if we were to look at those 3 overhead bits now and compare, and we see that W5s are not equal, the W6s are not equal, but the W7 is equal, that's going to tell us that there was an error in our message, and it was in W1. So what would happen if W2 had the error? How would we detect that? What's going to happen for the Ws 5, 6, and 7 if that second bit in our message was wrong? Right, so W5 and W7 are now going to be wrong, but W6 will be fine. Because notice there's no, that second bit doesn't appear in W6. Okay? And so likewise, if W3 is wrong, well, we notice W3 doesn't appear here in the W5, but it does appear in W6, and it appears in W7. And so we can compare, and there if we see 5 is fine, but 6 and 7 don't match, that tells us the error is in bit 3. Okay? So then bit 4 is wrong. What do we know about those 3 overhead bits? What's going to be the signature? They're all going to be wrong, because notice W4 is involved in all 3 of them. Okay, so now suppose, again thinking forward a little bit, that W5 is wrong. Okay, so we've gotten our 7 bits, and there's the error in W5. Are the 4 bits of our message actually incorrect? No, they're right. The error actually occurred in the overhead. But how can we detect that? What's going to be true if we now compare the W5 that we calculate versus the one we receive, the W6 we calculate versus the one we receive, the W7 that we calculate versus the one we receive? What's going to be true? What's the pattern if the error was actually in that first overhead bit? Exactly. So we'll notice that W6 and W7 are right because the 4 bits in our message are correct. Okay? And so we're going to compute the right sum. When we compute the big W5, that's actually the correct sum as well. But if the error came in that 5th bit, then it's going to be wrong. And so we'll notice that now the signature for the 5th bit being wrong is just only the W5s don't match. What's going to happen if the error is in that second overhead bit? Well, then it's just going to be W6 doesn't match. And lastly, if the error is in that 7th bit, W7 doesn't match. And so now you can look through, and if we assume that there's at most 1 error, there are these 8 different possibilities, because we can have either the errors in any one of the 7 bits, or there are no errors at all. And if we look for all 8 of those outcomes, is there a unique way to identify it by comparing these W5, 6s, and 7s? Yep, every one of those possible outcomes has a signature. So we can now take this message that's received, go through this decoding, and first of all, can we detect that 1 error? Yes, but can we also correct for it now? Yeah, because using this information, we can actually identify which position did that error enter. And so we know rather than having to go back to the sender and say, hey, resend that message, oh, well, we can look at this table and, oh, the error was in W3. Well, just flip the bit on W3, and we're good. I think that's kind of cool. Okay, so naturally, let's work some examples. So suppose you receive the message 0010011. What's the actual 4-bit message that was sent to you? And take a moment and think about this. You can assume that in all of these cases there's at most 1 error. Now go ahead and put a few things here up on the top for us. Just to carry over from the previous slides if you want those formulas. Anybody have an idea for A yet? What was the 4-bit message that was sent to you? Want more time to think about it, or should we start working through it? Yep, you've got an idea. Okay, so you think it was right that the 4-bit message was actually 0010. Does anybody agree with that? A few hands. Anybody disagree with it? Okay. Well, let's look through. That is, in fact, correct. Let's look through and see how we get there. Okay, so what we're going to do is we can sort of think about breaking this message up, and we're going to separate out those first 4 bits, what we think the message is, relative to those 3 bits at the back, which are this overhead. And so we can immediately identify now our W1 is equal to 0, W2 is equal to 0, W3 is equal to 1, and our little w4 is equal to 0. And then likewise, from our message, we get that the little w5 is equal to 0, little w6 is equal to 1, and little w7 is equal to 1. Again, we're just reading those 7 bits off from that 7-bit sequence we got. Now what we need to do is compare these 3 bits with these big W's written at the top of the slide, which is to say, given those 4 bits that we received, the 0010, what would we expect the overhead to look like? And we need to compare that against the overhead we actually received. And so our big W5 is just bit 1 plus bit 2 plus bit 4, and that comes out to be what? 0. Okay. So do the W5s match? Yep. In a similar sense, we can do the W6, where we have to look at bits 1, 3, and 4 of those 4-bit messages. And what is that sum equal to? 1. Okay. So do the 6 bits match? Yep. And lastly, with W7, we can add up its bits 2, 3, and 4. And that comes out to be 0 plus 1 plus 0 is 1. And they match. And so we notice now when we compare those little w's that we got from the message with the big W's that we calculated from the 4 bits, all 3 of them match. This will probably be a little bit messy if I go back up. Yeah, let me clear some of this off. But we can look at our table now and see when all 3 bits match, what's the case? No errors. Look at number 1 right there. W5s match, W6 match, W7 match. So we know there are no errors in that 7-bit string. And so if there are no errors, well, then we know that bit 1 was correct, and bit 2 was correct, and bit 3 was correct, and bit 4 was correct. So our 4-bit message was 0010. Okay? Take a moment and look at part B. I would be willing to bet that's not going to be entirely correct. Let me know when you think you know what the message is in part B. You want to have an idea? Yep. Okay, so you get 1011. Okay, so yes, that's correct, and we'll see that. But so now we see, so suppose we can go through this, and we're going to see that the correct answer, those 4 bits, should be 0 or 1011. So was there an error in this message? Yes, there was. Okay, so how can we go about seeing that? Well, just as before, we can identify our 4 message bits. So we get W1 is 1, W2 is 0, W3 is 0, and W4 is 1. And we can also read off what are those 3 overhead bits that we received. Our little W5 is equal to 0, little W6 is 1, and little w7 is 0. So now we need to go through and calculate what are those overhead bits that we expected based on the 4 message bits. And that big W5, in this case, is W1 plus W2 plus W4, 1 plus 0 plus 1, which gives us 0. Okay, so far so good. Those 2 bits happen to match. The W5s, there's no problem. Okay? When we get to W6, and we add bits 1, 3, and 4, what do we now get from our 4 bits in the message? We get 0. Okay, so notice now those W6 bits do not match, which is now telling us there is almost certainly an error. And so lastly, we can then look at our W7, looking at bits 2, 3, and 4, and when we add those together, we get 1, which notice also does not match the original bit we started with. So what we see now is that bit 5 was correct, but 6 and 7 were wrong. Let me erase this. We'll go back to the previous slide. And so if 5 is correct, but 6 and 7 are wrong, which case are we in? W3 is wrong. Okay? So if we come back over now, what that's saying is that bit 1 was right, bit 2 was right, bit 4 was right, 5, 6, 7, but bit 3 was wrong. And so we know we need to take that 0 and flip it to a 1, because that would make it correct. And so the 7-bit message that we really should have received was 1011010. And again, those first 4 bits actually constitute our message. Okay? So that's the 4-bit message that was sent to us, is that 1011. And we were able to use our code now to not only detect that, yes, there was the error, but we were able to determine which location it was in, and then we can just go in and fix it. Okay? So why don't you give part C a try, and we'll see what we come up with there. So going through this, what did you get for the big W5? So we got it 0, because we can look at our first 4 bits and we get 1 plus 2 plus 4 is 0 plus 1 plus 1, which is 0. No problem so far. What about our big W6? Also going to be 0, because we get 1 plus 3 plus 4, and 0 plus 1 plus 1 is still 0. And now for our W7 bit, what did we expect based from our message? Well, we're expecting 1, because we get 2 plus 3 plus 4 is, well, W2 plus W3 plus W4 is 1 plus 1 plus 1 is 1. This sounds a lot like, has anybody seen the movie Clue? It's a 30-year-old movie where they're arguing about how many guns are left in the revolver, and it's 1 plus 0, 1 plus 2 plus 1 plus 1 plus, or 1 plus 2 plus 1 plus 1. It starts to sound a lot like that. Okay, so what we end up getting is now our W5 matches, our W6 matches. Does our W7 match? No, it doesn't. Okay, so is there an error in our message? Yep. And we can go back to the previous slide real quick and see what's the case where 5 and 6 are correct, but 7 is wrong. It's right down here on case 8, which is to say W7 was incorrect. So we can come back to our message here. So do we have to change W1? Nope. Or W2? Or 3 or 4? Nope. What we end up getting is that W5 is still 0, W6 is still 0, and W7 should have been a 1, because that's where the error was. So what was the 4-bit message that was intended for us? 0111, which happens to actually be the message we got, but we didn't necessarily know that, and the error correcting code said, yeah, it's right. There was an error, but it wasn't actually in the message part, so you're all good.
So basically, if 1 through 4 aren't wrong, then it just stays the same.
Yeah. So remember, at the end of the day, so the question was, if 1 through 4 aren't wrong, then nothing happens. Right, because remember, these last 3 bits are just the overhead. They're not actually part of the message that was being sent. They don't carry information. They carry the context that are going to help us determine were there errors and where. Okay? Any questions on those examples? Okay. Then if not, I've got maybe one slide left to finish out the unit. Let me just erase all of this text. Okay, so sure enough, there are the answers that I believe agree with what we saw. And so the big idea now is these error correcting codes are quite nice because they can not only detect all of these errors, but they can actually help us correct for them as well, which can be good if we want to avoid having the sender resend information. But they tend to have a higher number of the overhead bits. So there's a trade-off. They're more powerful. They can help you fix the error, but you've got to use more bits to have them work. And so coming down to sort of this bottom block here of which code is right for you, again, it depends on what your situation is. When you're looking at what's the channel you're sending through, what type of information are you needing to communicate with another person, and some questions that you might want to take into account is how likely is it that an error is introduced? If it's very likely that an error is introduced, do you want to add a lot of overhead bits? Well, from some sense, yes, it's going to help you correct, but if errors are very likely, then adding more bits means you're going to have more errors, which means you have to be maybe a little bit more careful. Again, there's a trade-off. We might be interested, as we were trying to work through on Monday, what is the probability that at most one error is introduced during transmission? Because if we know that we're expecting maybe 2 or 3 errors during the transmission process, do we want to use something like this Hamming code that only accounts for 1 error? No. If we're expecting 2 or 3 or 4 errors, we should use a code that can handle 2 or 3 or 4 errors. Maybe we're interested in how expensive is it to send a message? Okay, is text messaging very expensive? No. For those of you that remember life before cell phones, was calling Europe on a landline expensive? Okay, from here, was calling California on a landline expensive? Yes. So do you necessarily want to have to make the phone call or to send a fax 4 times when you're paying MCI long distance charges every time? Okay. And so that might factor in. Again, maybe you're willing to bear with the cost of this extra redundancy because you want to avoid the actual monetary cost of having to resend the message every time. And then perhaps there could be time-sensitive applications where it's actually of interest. How long does it take to encode or decode the message when you're sending or receiving? Because maybe you need that information as quickly as possible. And I'm sure you could come up with situations where that might be the case. So with that, that is the end of our data transmission unit. Do you have any questions before we wrap up for the day? Yes? Can I go over entropy? Sure. So as I said, I don't want to go into a really formal definition because it gets a little complicated. But the idea of the entropy is to look at when we have like these 7 bits in our error correcting code with Hamming, 4 of them actually carried information. The other 3 were sort of these redundancy bits or these overhead bits. And so what entropy tries to look at sort of what's the ratio between how much information is actually in the total message that was being sent or received. Versus when we had like the checksum example earlier, there were the 4 message bits, but only the 1 redundancy bit. And so that ratio was maybe a little bit better where there's more information in the total message that we're sending and receiving. And that's the idea of entropy. Does that make sense? Other questions? Okay, then if not, please clear off your desks. Keep out a calculator if you so choose. And we're going to have a quiz. And just one other note while you're doing that, I'll just point this out now. It might be of help to you while you're working on your homework. For next Wednesday's quiz, I've posted this sheet of possibly useful information, just like we had with the GPS unit. So it's in here. It gives you, there's your probability formula, some binomial coefficients, and all of the rules for the Hamming code are here as well. It may be of use to you while you're working through your homework, but take a look over. And again, let me know if you have any questions. Otherwise, we will start handing out the quiz.